scrap my dx here. Okay, we're asked to find the area under the curve between 0 and 1 for this function. So to do that, we want to find something called the antiderivative. And the antiderivative is a function whose derivative would turn back into whatever you're trying to take an integral of. Okay, so we want to find a function that whose derivative would turn back into this. And actually, before we do that, let's simplify this using a property of integrals that we've studied. That 2 can come out front and multiply. And now we're considering something a little simpler for the antiderivative. Okay, so we got to think of a function whose derivative makes e to the x. And if you think back to when you've done the derivative of e to the x or any exponential function, when you take a derivative with respect to x of any exponential function, it's itself times a natural log of the base of the exponent. But natural log e is just 1. So the derivative of e to the x is e to the x. So the antiderivative of e to the x is e to the x. Okay, I wish the book started with a little easier examples. I'll make some more videos here though. Okay, and then I want to make sure I'm multiplying 2 to everything inside. That's why I put that bracket there. But I want to evaluate this integral from 0 to 1. So once I have my antiderivative, then I'm going to plug in those limits of integration. I'm going to plug in 1 in for x, and I'm going to subtract that by plugging in the lower integral, the lower limit of integration, the 0. And if you do that, e to the 1, this is e to the first power, so just e, and then e to the 0 is just 1, because anything to the 0 power is 1. Then we can distribute that 2, so our final answer is 2e minus 2. That's our integral.